Hi everyone, so we will solve this 8th worksheet today. Now you see the first question, we have a prime number p. We will show the only solutions of this congruence are the integers that are congruence 1 to modulo p and minus 1 on the same module. So what do we do? First of all, we have this. Now it means, by definition, p divides this subtraction, x squared minus 1. And we rewrite this parenthesis as in this form. So as p is a prime, in the course you should have seen this, as p is a prime and as it divides this product, okay, then either it divides x minus 1 or x plus 1. So if it divides x minus 1, it gives this by definition. And if it divides this one, again, we have this. So we get that the solutions of this congruence are these ones, okay? Either that or this. Now, for this question, we have a number a, which is not divisible by p, where p is a prime. We will show that no two of the integers between them are congruent modulo p. So what do we do? First of all, we suppose p doesn't divide a. We will prove by contradiction. And so we assume that NA is congruent MA modulo P. Of course, we suppose N is not equal to M, right? Because otherwise, if they are equal, then we wouldn't show this statement, right? We will show no two of these integers are congruent. So we need to suppose they are different. And of course, we take them between this interval 1 and p minus 1 because we have these numbers, okay? So what does it say? It says p divides this number, which can be written in this form. So p divides, as in the previous question, either p divides n minus m or it divides a. But we supposed before that p doesn't divide a, so here we have this. Now n and m are less than p, they are less than p, right? Because we chose them, we chose them between among these numbers, so they are less than p. And then this says if p divides the difference between them, then this should be n minus m should be equal to 0, right? Because they are less than p. So n, this gives if n minus m is equal to 0, then n equals to m. But we supposed before that n is not equal to m, so we have a contradiction. So this contradiction says that the assumption that you hold before, that you assumed before, is wrong. So what was the assumption? It was this and this. So it says, as this is wrong, then it says n and m are equal, and so there are no two integers among these numbers that are congruent, okay? Now we will conclude from A that the the product of these numbers is congruent modulo P to the product of these numbers, okay? Now we will use this statement to show this congruence after that. Now, by the previous parts, we know that no two integers among them are congruent modulo P. Now, we also know there are P minus 1 many numbers, okay, in this set. Now, as we have P minus one many elements such that or so that no two of them are congruent, then they should be congruent to these numbers, as they should be congruent modulo p. The congruence number should be less than p, and this congruence should be unique, right? Again, from the previous part we obtained this. Then what do we have? A should be congruent to b1 modulo p, till here we have that. Now this b1, b2, bp minus 1 should be in this set, okay, as we said before, and they should be disjoint, or not disjoint, they should be distinct. They are not sets, sorry. They should be distinct, okay, as we said, uniquely. So what does it say? Now we rewrite this start, these congruences. If we multiply all of them, on the left we will obtain this product, and on the right we will obtain these numbers, the product of these numbers. We know, for example, b1 is p minus 1, b2 is p, like that. It shouldn't be as an order, but we know uniquely, they are uniquely equal to one of these numbers. So we have this product, p minus 1 factorial. So we obtain this last congruence, okay, as we've done. Now we will use Fermat's Little theorem to compute these ones. Now this is the theorem, okay. So for this congruence, we suppose the greatest common divisor of A and P should be equal to 1, okay, where P is a prime, of course. So now we need to solve this one. Remark that p minus 1, which is 4, and this number can be written as in this form, 4 times 75 plus 2. Now, as 3 and 5, as in here, p is 5 and a is 3, the greatest common divisor of them is 1, okay? Then it means we can apply this theorem. So what do we have? Instead of a, we write 3. Instead of p, we write 5, as in here. And here we have 3 to the 302. So it can be written as in this form again, as we had here, this equality. Now, this is congruent to 1 in modulo 5. So here we have only 3 squared, which is 9. So it's congruent modulo 5 to 4. So we have at the end this congruence as we wanted to compute. These are homework, so it's easy, you see already. Now we will use the results of the previous part, and Chinese remainder theorem to find this one. Okay, here we're given this equality already. Now, if you compute these ones, so you will obtain them, okay, these congruences. Now, we have then this system, okay. We just apply Chinese remainder theorem, okay. It says there is a unique solution, and we have these congruences. Then we need to have this, because you know this can be written as in this product. So Chinese remainder theorem says this though, okay. And you see 9 is no, okay. So from these ones, for example, you will obtain these congruences. So for this one, it is, if we have 9 there, it is congruent to 2 modulo 7, so we can clearly write 9 instead of that. For here, instead of 2, we can also write 9 because it is congruent to 2 modulo 7. And similarly, we can write here again 9. So the solution is this. Now we will show 2 is a primitive root of this number 19. So here we have the definition. We compute the powers of 2, and we will see if we get the whole set, non-zero elements of this set. Okay. And for powers, we again only choose the non-zero elements of this set. Okay. So 2 to the 1 is again congruent to 2. And 2 to the 4, again, we have this. For 3, we have 8, right? You see, we have 2, 4, 8 there, the elements of this set. And 2 to the 4, we have the 16. And for this number, as we compute the congruence modulo of 19, we have this 13. So it's clear that we compute for all of them and get, you see, we have 1, 2, 3, 4, 5, 6. You see the non-zero elements of this set. So 2 is a primitive root of 19. Okay. We have again a definition. So it's the definition of discrete logarithms. So as you see here, you can read it by yourself. So we use this definition to find the discrete logarithm of 5. And this part is homework for you again. So 2 to the e modulo 19 should be equal to 5. Then if you make some operations, it's not that hard, you will obtain e equals to 60. Thus, as it satisfies this definition, then we say 16 is the discrete logarithm of 5 to the base 2 modulo 19. Now we will encrypt this message, watch your step, okay, by translating the letters into numbers, okay, as I noted here in the message. We have, for example, for A, we will have 0. For W, we will have 22, okay. So you just have the alphabet, so you start with A till the end to Z, you enumerate them, okay. And we will apply the given encryption function, this as in here, okay. And then we will translate again the numbers back to letters, okay. So here we have in this message. So first we will write these letters as numbers, as in here, okay. So for example, for W we have 22, for A we have 0, for T we have 19, okay, you write them. So for 22 we apply the function. For 22 we have 22 plus 14, and modulo 26 we have 10. So instead of 22 we now have 10. So for example, for 0 we have 0 plus 14, modulo 26 we have again 14. Now we keep continuing like this till the end, which is for 15. So for that we again compute modulo 26 and get 3. So at the end, finally, we have 3. Now we rewrite these, we don't rewrite, but we translate them into letters, okay? So as I said before, if you have the alphabet by starting 0 and computing like that, so you will obtain that 10 is K, 14 is O, and like this, you will obtain this message. So to say this message, watch your step, we have these computations, okay? And finally, we have these letters. So when you send this message, and the one who gets this message we'll apply the inverse of this function, and get this message again. Okay, so we encrypt this message. So the person who gets this needs to decrypt to obtain this message that you sent. Okay. Now we will decrypt the message. Okay. That were encrypted using this Caesar cipher. Okay. So the Caesar cipher, you need to know if someone talking about the Caesar cipher, you need to get this function. Okay. Now we have this. So as we will decrypt the message, we obtain the inverse of that. Okay, and it's this. So we're given this message. This is encrypted message. Okay, so we will decrypt this by using Caesar cipher. Okay, to get the exact message. Now we enumerate the letters and obtain that E equals to 4, H equals to 7, Okay, we only need the numbers for these letters. Now what do we have? For E we have 4, for O we have 14, So we apply this function. For example, for 4 we have 1 here, modulo 26. So we have this. And for 14, again, we apply this and get these numbers. Now we translate this to obtain the exact message. So for 1, we have B, because we set A equals to 0. Okay, remember that. And for 11, we have L. So the exact message, the message which is decrypted, is blue jeans. Okay. B and C are homework for you. And now we have these final 2 questions. So now it's something different. We will use RSA system, or in other words, RSA algorithm. Okay. Now we will find the original message, which is encrypted using this system, where n equals to this number and E equals to this. The encrypted message is this. Okay. So we will decrypt this message. Okay. So here we have a hint. It says to decrypt this message, first find the decryption exponent D, which is the inverse of E modulo this n. Okay. So we will find the modulo inverse of E first. So we have this number. Why do we compute that? Because D is between 0 and this number. What's this number? Remember the function phi before we did last week that. So it's phi of n. It's written like this. Or maybe we denoted it by this. I don't remember exactly. So what does that count? It counts the numbers of this set m such that m is less than n, and what else? And m and n is 1. The numbers that are co-prime to n. Okay. So what do we have here? And we also show that if this number inside of this function is a prime number, then we prove that it gives p minus 1. Okay. So we need to compute. We know that this d is in between this and phi of n, and it is phi of 43 times 40. 43 times phi of 59. So this is a prime and this is a prime, so it is this times this. Okay, here we have. So this should be in this interval, and also it should be the inverse of E, modular inverse of E, so it should satisfy this. Now if you use both of these equations, you obtain that D should be this number. Now as we will use to decrypt the RSA system, actually as the message encrypt using this, we need to apply these ones. So we will find the numbers m's using these ones. So we will use this encrypted 4-digit number, and we will get its power using this D. Okay, it says exponent, it's called exponent. So using this modulo this number, which is n. Okay, so if you compute this, you will obtain this number. So for this part, we get this number, and for this, again using the same things, we obtain these ones. Okay, and for the last 4 digits, always do this thing with 4-digit numbers. Now the message is then this. Okay, so we decrypt it and get this message. Now what do? We need to have letters. So for this system, we enumerate letters as in this form. We say A is 0, 0, B is 0, 1, C is 0, 2, da, da, da. K is 10, L is 11, da, da, da. Now, we know that S is, so each letter has 2 digits, right? So for 18, we have S. For 0S, for 08, we have I. Okay, so as in this form, we find actually the corresponding letter, and hence the message, which is decrypted, is silver. Okay, now this is the last question. I guess in the exam you will be given these numbers P and Q. Okay, so let's start. Now she wants to send this message, sell everything, but she also wants to encrypt this message. Okay, now and we will use RSA crypto system. So now what do we have? Again, we need to pick 2 numbers, P and Q, where their greatest common divisor is 1. They don't need to be primes, but they need to be co-primes. Okay, before we had prime numbers, but we don't need to actually have prime numbers. They should only satisfy this equality. Now as we have this P, okay, it can be written as the product of these numbers. So again, we compute, as I explained before, we have primes. If we have primes, then the function sends them to this number, the prime minus 1. Okay, so we have this. Now, why do we compute it? Because these should be in between 1 and this number. Okay, you can also pick 0, it doesn't matter. So the given message is this. Okay, so for S we have 18, for E we have 0, 4, for L we have 11, for L we have 11. So again, remark that we write them as 4-digit numbers. Okay, so we write everything in this form. Now as we want to decrypt this number, this message, sorry, we need to also compute these ones as we did before. So D is this, okay, because it should satisfy this. So we choose this number. Now, what do we have? It should be equal to this modulo this number. So we find all 4 digits, the corresponding numbers for all 4 digit numbers. And so the decrypted message is this, because for this number 1804 we have this number now. So we write that. For this number we have this. Okay, so we have this message which is a decrypted message for saying sell everything. Okay, this was the last question. If you have any question, you can attend the office hour, which is on Friday, okay, between 5 and 7 p.m. See you there. Take care.